Hello, and welcome to this video on parallel gap or series welding in the resistance welding playlist. To begin with, let me start by sharing the screen so you can follow along with the presentation. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies, which stands for Welding and Joining of Materials. Additional information on my consulting and training business is at welding-consultant.com. In this video, we're going to talk about parallel gap or series welding, a variant of resistance welding. Parallel gap or series welding, as shown in the photo below, is a process, resistance welding process, where both electrodes approach the part from the same side. This is done in situations where the other side of the part is not accessible, such as in a battery can welding. So parallel gap welding is a common process used for battery tab welding applications. Here you can see a battery can. You can barely see a tab. It's a very thin foil, usually sitting on the top. The two electrodes are coming from the same side. The two electrodes are electrically isolated, so the current goes from one holder into one electrode, into the tab, comes up on the other side, and goes back to the power supply. Usually, when for low current applications, a common use is for nickel tabs to be 100 microns thick. However, higher current applications may require thicker nickel tabs or composite nickel tabs, at which point you also need projections on the tabs to localize and focus the current exactly at the location where you want. Here's a schematic of the layout that I've shown on the previous photograph. This is a schematic. Here we can see that we have the battery tab on the top. So this would be your nickel tab. Battery can is the surface of the can where you're trying to weld the tab. And there are two electrodes, electrode 1 and electrode 2. They are shown as different color, indicating that the two electrodes can be of different material. They are shown of different size, indicating they could have different size. And they actually can also have different welding force. So this is unique about parallel gap welding compared to regular resistance welding. Over here in parallel gap welding, the two electrodes can actually have different welding force setup. This is obviously the only choice when the other side of the battery can is not accessible, as there are chemicals and components inside. So you cannot access the battery from the other side to make that weld. Here are some photographs of welds which have been made. This is a surface photograph of the battery tab after welding. On the right-hand side, you can see the welds have been made. There are 4 spots, 1, 2 over here, and 3 and 4. These 2 spots both had projections, and you can review the ideas about projection welding in a separate video in this playlist. And there are 2 projects on the bottom side. And these 4 welds were all done in the same sequence. So on the schematically, I'm showing on the right the footprint of the 2 electrodes. So they would have been rectangular electrodes covering the span of both projections. So there's one electrode covering 2 projections, the other electrode covering the other 2 projections. And during this process, the current would have gone through the electrode into these projections, into the battery can surface, come across, and then come back up through these other projections and make 4 spot welds. So as the nickel tabs become thicker, it becomes necessary to use projections. And it can be 1 projection on each side, and can also be 2 projections on each side. You also notice in this design that there is a cutout in the nickel tab. This is again made to prevent the current from shorting across the nickel tab. So instead of, if this cutout was not there, the current may want to short directly across and not be forced to go down into the can and then come back up. So the cutout has to be long enough that the alternative of going across is too cumbersome and the current will try to flow, go into the can, go through it, and come back up through these tabs. In some situations where we want higher current capacity, even a nickel tab by itself may not be sufficient. So here we use a composite tab. In this case, I'm showing the tab on the top. There was a projection on the tab, which has been welded to the battery can. And the scale of the battery can, you can see over here, is about 0.6 millimeters. And the tab is a composite, which has copper on the inside, stainless steel layers on the outside, and a nickel plating on the exterior, which you cannot see because the plating is too thin. During the process, the nickel plating melts and gets squeezed out a little bit, which you can see over here. You can see some elements of fusion on either side, but mostly a solid state bond. And you can also see a heat affected zone over here, which has been produced during welding. So the benefit of these composite tabs is that they are easier for welding because of the stainless steel on the outside. They are good for current carrying capacity because of the copper on the inside, and hence are quite well suited for high power applications such as in EV applications. Let's look at a little bit on the fundamentals of parallel gap welding. Here I'm showing you a schematic where you have, again, the two electrodes, component 1 on the top, component 2 on the bottom. And in the process, we supply a current of I, which is supposed to go through the weld and come back up on the other side. What is unique about parallel gap welding compared to regular resistance welding, that there are multiple current paths. So the current could go down into the component 1, short across the component 1, and go back up, and not at all go into the component 2. In that case, there won't be any welding. So what we are trying to do is set up the process conditions as such so that more of the current goes into the bottom component and comes back up. So we want more of I2 than I1. So that way we get 2 strong welds at these 2 locations. So how do we go about trying to increase amount of I2? So one of the ways to increase I2 is increase the resistance of the top tab. If the top tab has high resistance, then the current would try to go short down into the bottom component and then come back up. Another way is to make the top component as thin as possible. So if the top component is thin, then again, it will be easier for the current to go down and come back up. Another option is to increase the gap between the 2 electrodes. Wider the gap, more likely that the current will rather go down and come back up rather than going through the top tab. Of course, all of these factors work together, and so you have to design the process suitably so that you have a robust welding procedure. Here's an example of a cross-section of a parallel gap weld where you can see the top tab, which is thinner, and the bottom tab, which is thicker. So that helps to push the current down. You can see in the cross sections, you can see the nickel plating between the 2 has been disturbed over here, and the nickel plating also has disturbed over here. You can also see a heat affected zone where the contrast is different. You can also see a heat affected zone where the contrast is different. And that shows you that these are 2 separate welds. So the current would have gone down from the top electrode, from the left electrode, and go down into the 2 components, flow across, and then go back up. So you can make 2 separate welds if the distance between the 2 electrodes is wide enough. If the electrodes are fairly close, these 2 welds can sometimes actually combine and look like one big welding location. You can also notice that in the metallurgical cross sections, as well as mechanical testing, you might find that one of the welds on one side is slightly weaker than the other. And this is due to the effect of polarity. which we will review in another of the videos in this playlist. And you'll find that one side of the weld is weaker than the other because of the directionality of DC current. And this is not unusual. This is quite common in parallel gap resistance welding. So parallel gap resistance welding is a common process in battery welding application. And it can be used in any situation where the other side of the weld is not accessible. It doesn't have to be just batteries, but battery can welding or tabs to battery can is a very common application. Process control is a little bit more difficult than regular resistance welding because of this phenomena where you have multiple paths for current flow. So in regular resistance welding, there's only single path for current flow, whereas in parallel gap welding, you have two options, I1 and I2. And so it becomes a little bit difficult to control the process to make sure more of the current flows through I2. However, there is no independent way of measuring how much of current flows through I1 and I2. Process is able to make two welds. If the gap between the electrodes is wide enough, you can actually make two spot welds. And of course, if you're using multiple projections, you can actually make four spot welds in one shot. So that way the process is very efficient, that in one stroke, you can make multiple spot welds. So this is the introduction to parallel gap welding, a very unique resistance welding process commonly used in battery applications. Thank you for your time. If you are interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking on the button below. And there are other videos on different topics in these playlists, so feel free to review those as well and enjoy that information as well. Thank you for your time and wishing you the very best.